Imagine you are designing a complex machine or a sophisticated electronic circuit. You need to ensure it operates smoothly and predictably, without oscillations or runaway behavior. That is where stability analysis comes in, and the Bode plot is often one of your go-to tools. However, it is crucial to understand that Bode plots, while incredibly powerful, do come with specific limitations. Primarily, their direct application for stability assessment is most reliable for linear time invariant systems that are also minimum phase. They struggle with non-minimum phase systems, offer limited insights into absolute stability, and are not directly suited for nonlinear systems or systems with significant time delays. The core reason for these limitations lies in the fundamental assumptions behind Bode plot construction. Bode plots graphically representing the frequency response of a linear system. A key assumption for easily interpreting stability from gain and phase margins is that the system is minimum phase. This means it has no poles or zeros in the right half of the complex plane, and, crucially, no pure time delays. When a system is non-minimum phase, for instance, due to a right half-plane zero or a transport delay, the direct relationship between the magnitude and phase response breaks down. This can lead to misleading gain and phase margins, potentially indicating stability where instability exists, or vice versa. Furthermore, Bode plots are inherently a linear analysis tool. They cannot accurately model or predict the behavior of systems with nonlinear components like saturation or hysteresis, where the output is not directly proportional to the input. Finally, while they provide excellent relative stability indicators like gain and phase margins, they do not directly give information about the system's time domain performance, such as overshoot or settling time, which are critical for practical applications. So, how do we navigate these limitations in practice? First, always verify if your system is minimum phase before solely relying on Bode plots for critical stability conclusions. If you suspect or know your system has non-minimum phase elements, like a time delay, then consider augmenting your analysis with other powerful tools. Nyquist plots, for example, offer a more comprehensive view of stability for non-minimum phase systems, as they encircle the -1 point in the complex plane to determine stability. Root Locus plots are another excellent alternative, focusing on the pole locations in the complex plane as a gain parameter changes, directly revealing absolute stability and transient response characteristics. For systems with significant nonlinearities, specialized techniques like describing functions or phase plane analysis are often employed. Moreover, modern control engineering heavily leverages numerical simulations, which can provide insights into both linear and nonlinear system behaviors across various conditions. Understanding these nuances truly elevates your control system analysis. For example, a common non-minimum phase element is a right half-plane zero. These often arise in systems where an initial undesired response occurs before the desired response begins. Think of a chemical process where applying heat initially causes a drop in temperature before it rises. Another example is a transport delay, where a signal takes a finite amount of time to travel from one point to another, common in remote control systems or long pipelines. These specific system characteristics can severely undermine the straightforward interpretation of Bode stability criteria, making the use of complementary tools not just an option, but a necessity. The ability to identify when a Bode plot is insufficient is a mark of a truly skilled engineer. By appreciating the specific conditions under which Bode plots excel and acknowledging their boundaries, you gain a far more robust and accurate approach to control system design. This deeper understanding enables you to strategically select the most appropriate analysis tools, ensuring the systems you build are not only stable but also perform reliably and predictably under all relevant operating conditions. It is all about building confidence in your designs through informed tool selection.